Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, today we're going to look at techniques to measure the ionization parameter. The previous video, we talked about the ionization parameter itself, and we showed that determines the level of ionization of the gas. We did H plus over H naught, and we had a look at oxygen ionizations and some other things. What I want to do now is think about how to use a telescope to actually measure this. And so let's go back to our very u.n. And so we've got set a prefix that's not going to change. Black body, we have a grid over ionization parameters. We're going to change the ionization parameter by 8 orders of magnitude. I've changed the density to be 10 to the 3. It won't make much of a difference, except we want the forbidden lines we're going to be working with here to be nice and strong. More on that later. So this is to get the model to run, set the R0, sets on top zone 1. That makes a very fast little compact model to do. I'm going to save the grid points because we're going to make plots where we're varying the ionization parameter. The grid file has the ionization parameter values, and it also has a summary of the error conditions in the plot. And save the overview because that had the oxygen and hydrogen ionization, among others. So we made an ionization plot. The new command here is the save line list command. We've talked about that in a previous video, and you can save line list relative intensities, absolute intensities. This time we're going to do a line ratio. This is going to tell us the ionization parameter. The way this works is I done set save prefix, so the output file, the thing we're going to create is going to be very u.lrat for line ratio. I always call it that so I can remember it. So you think of this algebraically, so left equals right. So the right is going to be linelist.dat, and that's going to be a file that's going to give the line ratios that we want to work with. So let's go have a look over there, linelist.dat. Okay, so going top down, these are line pairs. So what I did is I looked in the data directory. We have a series of linelist.dat files, and there are files where I've gone through the output and cherry picked out the strong lines for different environments. This happens to be from line list NLR.dat, so narrow line region. But it is an HQ region. You can look at any of these line lists. It just makes it a little bit faster because you have to get the right wavelength and you have to get the right label. So I just copy paste from one file to the other. So what do we have here? Blends, these are pairs of lines of the same element and organized so it's a higher to lower ionization stage. So the first blend we see is 1549 to blend 1909. A blend in cloudy is an unresolved line that's two or more lines together. Blend 1549 is the carbon 4, so that's carbon plus 3. And it's a pair of lines of the same multiplet. They're very, very close together. Blend 1909 is carbon 3, so carbon plus 2. And there's two lines that are close together here. And so in most telescopes, you would just see a single line that's called a blend. And in some cases, it's also the same as a multiplet. So this is carbon 4 divided by carbon 3. By convention in cloudy, we use vacuum wavelengths for less than 2,000 angstroms. So we didn't actually need to specify this. So these are some more blends. This is nitrogen 4 divided by nitrogen 3. So two stages of ionization of the same element. We want two different ionization stages. Doesn't have to be adjacent, but we want to see the ionization of the gas change and make these line ratios different. We want to use the same ratio, the same element in the ratio, because we don't want to get into questions about the composition of the cloud. So if you divide nitrogen by nitrogen, you don't particularly care what the oxygen is. Speaking of oxygen, here's O3 divided by O2. So this blend is the 3727 doublet. Another pair is neon 5 and the near ultraviolet. This is neon 5 divided by neon 3. So it's not adjacent stages of ionization, but they'll prove interesting. If you go out into the infrared, here's the nitrogen 3 line at 15 microns, and we've divided by the nitrogen 2 line at 12 microns. And all these lines, you can enter a hash mark and then enter comments after that. So let's get out of that. So what I'm going to do now is run this guy, and then we're going to have a look at some output. Okay, it's finished. Let's check the uh, grid points to see that everything worked. So the first two columns are false. They're all false, so there are no failures, no warnings. Then the exit code in the very center is a bunch of OK. So this means it is exited OK. The last thing we want from this grid point is we're going to get the values of the ionization parameter. So that's the second to the rightmost column. So we'll use that as the x-axis in what we're going to plot. Now let's look at the new file. And what this is, in the first column in blue here, gives tables of line ratios. So the first one was blend 1549, and it was divided by blend 1909. And so that's this column here. So we're increasing the ionization parameter as we go down. And we'll notice that the carbon 4 divided by carbon 3 has gone from 10 to the minus 4 to 10 to the 7. So that's 11 orders of magnitude in line ratio that has changed here. So that what that tells you is that this line ratio is extremely sensitive to the ionization parameter. They all are. All of these ionization parameters, all these line ratios have very powerful dependence. This is 9 orders of magnitude. This is the nitrogen 4 divided by nitrogen 3. This is O3 over O2. So you see another 11 orders of magnitude. So it's a very, very powerful indicator of something. So what we're going to do now is make a plot. So let's go over to views. This is a views plot we started before. We used the overview file to show the temperature as a function of ionization parameter. So the density is being held constant. So the radiation field, the top of the ionization parameter ratio, has been changed by 8 orders of magnitude. So there's a big change in the brightness. And you see here the kinetic temperature did not change by a factor of 2. The temperature is not very sensitive to the ionization parameter. What is fairly sensitive is the ionization of the gas. We've made this before. So this is the oxygen ionization. So this is in the save overview file. And so we started out with atomic oxygen here, not a whole bunch. O plus peaks at the lowest ionization parameter. O plus 2 is this is O3 peaking at this ionization parameter O4. So we see that each of these ions have a different peak ionization parameter. And now we're going to look at some line ratios. So the way I did this is I really start out with the ionization plot, but then I changed columns. So I read in the LRAT data file. So we're going to leave the x-axis at the ionization parameter right over here. And now I'm going to choose a line ratio as the y-axis. So this is a nitrogen 5 over nitrogen 3 over nitrogen 2, nitrogen 4 divided by nitrogen 3. I'll get it out. And then what I did was copy this part of the string from that line label and pasted it in this key text here. So I went through and did it for all the lines in that save file, and it was originally in that data file. So then we end up with a series of these line ratios. Let's look at the plot. So this is from top to bottom 15 orders of magnitude. So this is a huge range in the vertical axis. We see that each one of these line ratios is an extremely powerful diagnostic of the ionization parameter. So if you wanted to measure the ionization parameter, I'm not quite sure why you'd want to do that, but if you did, all you'd have to do, if you could even measure this line ratio to a factor of 2, you would determine the ionization parameter at very, very high precision. Not too many people actually care about the ionization parameter, but this is the driving physics but behind seeing emission lines change in the spectrum. So this is the kind of the kernel physics that's making line ratios, ionization ratios change. And so if you've set up other parameters, perhaps parameters you care about, like the SED of the star, if you then see the line ratios changing, is almost certainly because something related to the ionization parameter has changed. So the takeaway here is the line ratios in the spectrum are very sensitive to the ionization parameter, some kind of intermediate head stuff parameter that's in the code, it's in It's in the physics. This is how nature works. We don't get to decide that question. What you may care about is something like the brightness of the star, the temperature of the gas, these other things. So the ionization parameter we saw does not greatly change the temperature of the gas. We're going to start talking about now in the next video is what does change the temperature of the gas, and it's going to be something surprising, the shape of the SED. So see you next time.